Hey, you're tuned in to Pop Goes the Stack, where we explore emerging tech like it's a cursed artifact. Curious, powerful, and probably going to break something. I'm Lori MacVittie, and I brought backups. I also brought my co host, who we're still trying to figure out if he's AI or not, Joel Moses. And today we have a returning guest from earlier episodes, Dmitry Kit. Dmitry, welcome.
Glad to be back.
Awesome. Well, you were perfect as a guest for this particular topic because today we're talking about, well, of course, we're talking about AI, but everyone else is chasing generative AI for flash, for productivity gains, all the good things. But the quiet revolution, the one that enterprises can, actually monetize, use, apply more broadly, is on the predictive side, right? Traditional, classic, the words we use, to describe the AI that we've been doing for a long time before LLMs made their big splash. And recently, there was a company, and they used, a more traditional approach to uncover the right formula for a paint that can passively cool buildings by up to 20 degrees. That's cool. Just paint it and it gets cooler.
Yeah.
Like I'm on this. I know you were in the code, Joel, and I know
Hey, look, all you got to do to get me to a party is talk materials engineering, and I am so there. Before we get started, I think it's really important to realize the importance of what we're talking about. So, the story came out, and this paint helps make buildings 20 degrees cooler, and it's a breakthrough in terms of the material that was discovered that could actually do this. But let's reverse course just a little bit and talk about the early part of the 1980s when. Through a great deal of pain and discovery process, a lot of trial and error, they discovered a new chemical formulation called lithium cobalt oxide, and that became the formula that was incorporated into what we now know as lithium-ion batteries, and those have changed the world. I mean, the density of lithium-ion batteries has enabled us to drive cars that are electric and have good range and that sort of thing, but the discovery of lithium cobalt oxide was almost by accident. And so moving material science from trial and error, I'm looking for something with a specific set of properties that has a specific valence charge or has a particular characteristic, is a lot of trial and error on the part of the experimenters. And the great thing about artificial intelligence is it doesn't ever get tired of the churn of experimentation. And that's kind of what we're going to be talking about today. The revolution in materials engineering brought on by something called generative adversarial networks. Dmitry, what is a GAN?
Well, and just to follow up on that, a lot of these things do come through experimentation, and taking that idea that you mentioned before this paper, the way that scientists looked for these materials was by defining the design space, like what materials are possible, and then searching through the space and then simulating the results to see um, if it produces the kind of things that they want. And as they produce more and more of the things they want, they start focusing more and more on that space. And in the paper, they mentioned using genetic algorithms, right? Which is sort of the way to search the space. And that's usually a slow way to do it.
Right.
The approach that was taken in this paper is incredibly novel, in which they trained, again, a generative adversarial network to produce designs based on the kind of properties you want. So instead of searching in the design space, they're saying, look, we want materials that have this kind of reflect heat in these kind of in this kind of manner, and then they can sample from GAN to generate a whole bunch of possible materials that do that. And then taking a few of those samples, they can simulate them and actually see if it is in fact producing the kind of properties that they want. And by training the GAN to produce these things really well, they were able to generate 2,000 potential designs a second.
Wow.
And so, and because they already knew that the GAN was already in the right spot for the properties that they wanted, they didn't have to search all 2,000. They just could sample a couple, and they did produce real world materials, and they demonstrated that the GAN was actually in fact producing the things that they expected.
Wow, that's kind of impressive.
Well, now you still have to explain. So back when I was in college, and granted, like it was a long time ago, there was just neural networks, NNs. That's all there was. Now there's GANs, CANs, CNNs. Who else? All right, there's a ton of them. So we're talking about GANs. So what is a GAN specifically?
Right. So a GAN is a neural network that, and then particularly they use conditional GANs, which you give it the label, which is the properties you want, plus some noise factor. And initially, a GAN produces some random output. Because it hasn't been trained, there's random weights in this neural network. And especially because you're introducing noise as part of the input, it's just going to produce noise on the output. So what they did have, and we haven't talked a little bit about this, but they trained a neural network to do forward simulation. So given the design that this GAN produces, it can actually tell you whether what properties this material will have or predict it. And so that's one of the signals you have. The other one is what's called the discriminator, and that's part of the usual GAN framework, which is the discriminator is supposed to say whether the input it's receiving is that coming from real data or fake data generated by the GAN. And so what the authors did was they combined the prediction of the neural network that said, here's the kind of properties we expect this design to have, and the discriminator that says, oh man, this is completely fake. Like this doesn't come from a real distribution at all. To then go back and say, okay, how do I modify my outputs such that I trick the discriminator to think that I came from the real data set, as well as match the properties that the neural network is predicting to the properties that were given to me in the first place, right? Because that's what I'm trying to recreate. And so using backpropagation, standard neural network training paradigm, you change the outputs of the GAN such that it starts looking more and more like the thing you expected to produce. But because you keep adding the noise at the other end, it's never going to be the same thing that it produces, but it's supposed to be in the kind of the same space, right, of designs that you expect to get for those kind of properties that you expect to get.
Right. I heard a statistician friend of mine call GANs Fight Club for numbers, which I thought was kind of an interesting way to put it. But it's essentially creating out of randomness, guided by a set of parameters, things that adhere to those parameters most closely by first of all perturbing the input and then running itself against itself, so to speak, which is an interesting way to do it. Now, this technology is actually released into open source. I believe it's on Microsoft's site. It's called MatterGen, and MatterGen looks like it does a number of other things. The technology the researchers are talking about is generally usable for all sorts of materials engineering. So, if it can formulate paints, what else do you think it can do, Dmitry?
Well, this is the interesting part of this work is that they trained the simulation net, right? So the problem with exploring the space traditionally is that you still need to confirm that you are producing what you think you're producing,
right?
And that takes time. It usually takes fluid dynamics or whatever it is. So here the way they designed the design space allowed them to train a simulator that could evaluate lots of designs very quickly. Yeah. And I think that's applicable potentially to any kind of physical simulation systems. So material science is definitely, I think that opens up a lot of doors for any kind of material science research, which I think is what makes this amazing work. But we can think about any other place where, fluid dynamics or any other kind of physical systems where right now we have to run these really large, simulations on graphical cards to try to predict what's happening. Maybe we can, train neural networks of the right design.
Yeah, I think that's an interesting thing to note. They call it the flywheel approach. So you have MatterSim, which generates things according to the attributes that you want them to have. So it generates a guess at what the molecular structure might look like, and then MatterSim, which goes through and says, does it really do that? And both of them use different branches of artificial intelligence in order to get to that. I believe that given the design specifications, they are seeing relative error below 20%, which means that for the most part, the bulk of what is being generated is something that has those chemical properties, which is remarkable. If you can translate this into other domains, it's going to have a profound impact. We've already seen this type of approach being used to formulate new drugs, like mRNA, for example. But the design of batteries, fuel cells, digital signal processors, all of them can use this mechanism. It's an exciting time.
Well, who else could use this approach? I mean, fundamentally, the difference between what they're doing and what an LLM doing is an LLM, right, is predicting words, and this is predicting certain properties in materials, which Joel will go on about if we let him. Right? He really
Super
will.
exciting.
We'll have
Super
a
exciting.
special episode just for Joel to talk about material science. But in the enterprise, most people aren't designing paints or material sciences, right? They buy their paint and they buy their batteries, but there are uses for this approach as opposed to just relying on an LLM in the enterprise. But the question is, so what kind of data or problem set, if I'm, in IT, might be well served by this kind of approach versus just a chatbot? Dmitry?
So obviously, cybersecurity is more of my area of expertise. And when we look at those signals like packets and bits, they contain structure that's not necessarily language, or at least not necessarily in the form that the large language model was trained. So including like tokenization. Even if we look at strings in terms of like what's being executed or what requests are being made to a web server, that data has a very specific structure, and it actually is quite limited compared to the space of the entire English language or any language. And so it is possible to come up with very efficient and effective solutions by starting from the first principles of, here's what my data is, here's how it's distributed, and then building up a solution even in this form, right? And we've used data encoders and generative AI to generate signals like the signals we expect to see in the systems that we are monitoring, so that we can then detect when we're seeing things that are not the kind of things that we've seen in the past. So kind of anomaly detection type approaches. I will also say that reinforcement learning with human feedback actually uses this idea of training a simulator. Getting people to label things, that's expensive and doesn't quite scale. So when you get enough people to label enough things, you can train a neural network to behave like people, and then you can reinforce a large language model with a neural network that runs a simulation of a person at the other end of it. So this idea of training, a stand-in basically for a simulation is an incredibly powerful idea.
Especially in security. And in fact, right before we started actually recording, we were kind of walking through some of those things, and Dmitry basically had an insight. He didn't say it in the same words, but it was his insight really that one of the reasons that LLMs work well with a lot of web traffic and APIs is because it is language, right? So you can see it, but it is a more limited set, right? Because it's structured. HTTP has a structure, JSON has a structure, data has structures. The key, I think, as we move forward to agents and agentic that start actually using LLMs to generate things and ideas and conversations, is that's no longer structured. So you almost have to work toward an approach that leverages both in order to advance cybersecurity in the AI future that we're all heading toward, right?
That's that's good. And another way to put this is that large language models are incredible. They have a lot of knowledge, but when we start working with very specific applications, there's a lot of structure that we can use to reason about that data. And if we come from the perspective of a large language model, then we're trying to get the large language model to emphasize those structures, to focus on those structures that you wanted to reason about. Like, this is an attack, this is not an attack, or whatever it may be, the application. Whereas if we go from the other perspective, we can say, let's actually like already start from the structures that we have and encode them into the machine learning models, and then have them really focus in on that. So, and I think it's both. I think at the end of the day, the answer is probably both.
Definitely. Well, it's great, and just to put not to put too fine a point on it, but the model that was used to create this new paint was roughly 600,000 parameters. It's not a huge model, and it's just because of what Dmitry's talking about. They applied a focus on the characteristic that they were really interested in, not a general language characteristic, but the way that interconnections work with materials and molecules. And that model can be relatively small and produce. I believe the known error rate there was 20%, which means that your search space for the property that you're looking for is diminished hugely by generating things that apply to it. It's an exciting space.
Yeah, and they can probably run on a lot less powerful hardware as
Absolutely.
well, right?
Absolutely.
So,
In fact, I think the Microsoft package says that you can run it quite well on Apple Silicon, which means MacBooks.
hey, well, I got one. I'll try it out sometime.
I believe they use the 3080 video. So
Very nice.
Well, it's getting late, and this has been a great discussion. I learned a lot, including that Joel really likes material science. I didn't know.
It's
I didn't
lovely.
know. But if there were three things you wanted to leave listeners with, and they're not all material science folks, right? I think they're probably technologists. Like, what three things did you learn you think they should walk away with, Joel?
Well, I first of all, LLMs are good for more than just chatbots. I think that we kind of gravitate towards the thing that we interact with most readily, and that would be a chatbot. But generative adversarial networks and reinforcement learning and things like that, which are not quite as sexy, at least from an interactive perspective, are still not only usable, but we're finding new breakthroughs with them all the time. The other thing is that the technology is broadly applicable to things to help people design and find a way to search large amounts of data very quickly for things that have less error. And that's huge in the area of cybersecurity, the design of new drugs in the pharmaceutical industry. We haven't begun to see what has happened. As I mentioned, in the 80s, it was the discovery of one lithium ion salt over the space of years and years of research into battery technologies that broke open the ability for us to drive electric cars today. So I'm excited for what happens in the future with AI on this.
Cool. Dmitry, what is it you think people should take away from this?
so I think as we got into deep learning, we sometimes forget that the data is important, and understanding what the data is and understanding what your problem is, especially when things don't behave in the way you expect them to, sometimes it's important to pull back on, well, what am I feeding it? Like what am I, inputting into the models? So I really like this collaboration that these authors had with multidiscipline with computer scientists and so on, that where they really understood what their problem is, created a design space that really made sense, and that allowed a lot of these machine learning tools to just eat it up and produce amazing results.
Awesome. Once again, garbage in, garbage out.
You
It's
are
so
what you eat.
there you go. Yes, you are what you eat. I like that. Well, that's a wrap for Pop Goes the Stack. If you made it through unscathed, hey, subscribe and share with a friend who loves danger. We'll poke the next gremlin very soon.